This is one of our speakers today, Mike Whitehouse. Come on camera and introduce yourself for us.
Sure. Mike Whitehouse here. I'm with ISCO Industries. Very honored and privileged to be here. I started with ISCO in '92 in the sales department. I then went to fabrication, from there to design and engineering, and I'm currently focusing on codes and standards. My degree is actually in geology, so I'm a rockhead that found a happy home in plastics.
All right, everybody out there, do not challenge him to name the most number of rocks possible in 30 seconds, as he just steamrolls everybody through that process. Now we got Doug Keller and Stephen Burrows. We want to come on and tell us who you are and give us a brief introduction. Doug, you're first there.
Hi, I'm Doug Keller with LyondellBasell. We are a polyethylene and polypropylene resin manufacturer. So I do a lot of work in codes and standards as well. Work with the Plastics Pipe Institute, ASTM, AGA, AWWA. Have 32 years, coming up on 32 years of experience in the polymers industry.
Doug's goatee is also longer than mine at this particular junction, so I might have to work on this one a little bit. Stephen? Whoa, Stephen,
afternoon,
what's that
everyone.
behind you before you tell us who you are? What
Yeah, thank you. Good afternoon. I'm Stephen Boris. I'm Vice President of Engineering at Pipeline Plastics. We are a polyethylene pipe manufacturer headquartered in Texas with plants around the country. We make up through 65-inch diameter for all sorts of applications. Yeah, the picture behind me always gets some notice. It's been called a lot of things, but what it actually is some cast iron pipe that was pulled out of Texas, actually just a couple of years ago, when we used polyethylene to replace their cast iron line that was bringing the pipe through Childress, Texas. And so this is some of the stuff they were using for decades, and this is what their clean water was going through. So not always the prettiest, but that's the reality we have.
So a lot of times, if the American public saw pictures of that, they would probably want some immediate change, right there, Stephen?
Well, I would.
All right. So here's the bench that we've got working for you as well. So that's me. I'm a civil engineer here for the Alliance for PE Pipe. We have Dan Landy and John Darius Stevens, all answering your questions behind the scenes here. Take a screenshot of this. You're welcome to contact any one of our experts through this process. Well, we really do welcome those questions that you have, and they'd be happy to work with you. We love to talk about high density polyethylene. So definitely send us a note about your project and include the Alliance or any of our presenters in development of your project through that. Here's a general overview of what we're going to talk about: site pipe management, above ground behavior. High density polyethylene is a viscoelastic material, so there are some unique aspects about high density polyethylene with thermal and Poisson's condition, which I mentioned earlier, but that behavior is very well understood, and we've designed many projects with them themselves. So then we'll shift and focus on above ground installations to help give you tools that really can help you make sure that you're successful in your installation as well. So Stephen, I believe you're first up here for site pipe management as we go through it, and tell us about transporting and receiving.
Yeah, thanks, Alan. So let's just start off with the basics. So the pipe's got to go from the plant to the job site. So it has to be transported there, typically on a flatbed truck. Typical lengths, I would say 90% of what we make are 50-foot joints. 40 foots are also available, as are 53-foot joints are sometimes available depending on the shipping conditions and where the pipe's going and size and things like that. But 50 feet is what you would normally get from the plant to the job site. Moving it, storing it, dragging it, we'll talk about that a little bit, and potential for pipe damage and what do you do if you have that, and then some productivity tools on the job site to just make the job a little bit easier. Predominant method for moving polyethylene pipe around would be a forklift or a telehandler with forks on it. First of all, make sure the forks are clean with no burrs and jagged ends. I've seen people put foam around them. I've seen them put pieces of polyethylene pipe around them to protect the pipe from the forks. You don't typically need to, as long as they're in good condition, but you can. Make sure you use a wide setting on those forks because you are dealing with a 50-foot joint of pipe. And also, when we bundle this, you will at the plant, it'll come in bundles. That means the pipe's going to be strapped in bundles together. Could be as many as 5 or 6, could be as few as 2. But pipe bundled together is a whole lot easier to move and handle than single sticks. Single sticks, pipes round, it rolls back and forth on forks if you're not careful, moving forward and backward. So if you can move it around in the bundles, it's much easier. And then when you have to pick up single sticks, take more caution and or use lifting straps. So of course, as you're moving things around, anytime you lift things in the air, look out for overhead constructions on both sides, 50 feet on either side of you. Need to make sure all that is clear. Inspect your riggings for damage. Like I said before, straps are the #1 method we like to use in moving around single sticks of pipe. Again, forklifts can be used, just with more caution. Be careful swinging pipe over workers. Yes, it is plastics, and yes, it is lightweight, but a 50-foot stick of 24-inch polyethylene pipe can still weigh over 3,000 pounds. And so that can do some damage if it does hit someone or falls on them. So just be careful and use all on-site safety protocols as required. Utilizing your nylon slings, make sure they're in good shape. They're not frayed. They're not worn out. Again, these sticks can be several thousands of pounds. So just be careful when you're lifting them. Lift from the center. You could use 2 lifting points for longer sticks and delicate moves if you need to. But chains and wire lifts and cables are not preferred for polyethylene pipe. We always recommend to go with nylon strapping such as this to minimize any potential damage. So you're going to want to normally stage the pipe in different places for your job site. So you'll come in bundles off the truck. You can offload those bundles fairly easily. Do not push them off the truck. Lift them off one layer at a time or one bundle at a time and place them in a prepared site, such as you see here in the pictures. They can stack very easily that way. There's usually timber or lumber separating each of the layers to make sure you can get forks in and out of there easily. But it's much easier to store that way and to move around as you move it to the different job site locations for actual use. The picture on the right does show some bundles that have been broken and some boards that have been broken, moving the pipe around. As you can see there, it becomes a little more difficult to handle once that occurs, and you'll just need to take some more care. Forks are a little bit harder to use in that case, so it may take straps and maybe more than one on each end to move those things around when they get to be in that shape. Well, if you are stacking your polyethylene pipe, there is a stacking charts that are available. There's a field manual put out by the Plastics Pipe Institute for municipal applications. There's also the PE Pipe Handbook, which if you don't have, you should get a copy of that, which gives this guidance as well. You can see here the smaller diameter pipe, 4-inch. You can store it several layers high. Because it's much easier to move and store that way. As you get into the larger sizes, though, the number of layers you can put then becomes reduced to minimize the amount of force on the bottom layers. But if you're stacking as DR17 or less, which is typically what you're going to be using for municipal applications and some industrial applications, you will see those bundled together on the job site. If you do have to break those bundles, make sure that your bottom boards are supported and off the ground, or your bottom pipes are off the ground. And you have some stops in there to keep them from rolling and scooting out from under there. Again, you can see job site management is always very important. Once these things become broken and distributed that way, as with any construction product, it's just going to make it more difficult to manage and move around carefully. So just make sure you use proper job site management and move them around as minimally as possible. So once you get the pipe put together and moved around, it's not going to stay in one place. You got to get it to where it needs to go. Since polyethylene is used in directional drilling applications predominantly, or in many cases, long strings are put together. And then as a pipe is utilized or put into the trench or pulled into the borehole, if you will, it can be pulled along the ground. While not a preferred method, because the grounds are all different, you could have jagged rocks, you could have very smooth surfaces such as these. The polyethylene can be pulled on there. You'd be surprised how minimal amount of damage you do get on polyethylene when it's being pulled down a city street. Down jagged rocks, you got to be a little more careful. There are other ways to do it, but this is permissible as long as you are watching the pipe carefully for any excessive damage. I think we had a little video there, but so what are we talking about with damage? Again, polyethylene pipe's extremely tough. It's hard to damage, but if a big rock gets in the way or a fork tooth gets in the way or a bucket tooth gets in the way, it can gouge or scratch up the pipe. There is good rules of thumb out there. General guidance has been supported by research and testing that as long as you have less than 10% of the wall thickness, so 10% of the entire wall, if your gouge or scratch is less than that in depth, you can leave it alone. It's going to be benign to the pipe. It won't see any damage. It won't see any reduced performance from that. No need to cut it out. If it's deeper than that, it's recommended to cut out that section. You can fuse it right back together and still have a monolithic piece of pipe. Again, if you're in doubt, you don't know, easier just to cut it out and use a fusion to put it back together and move forward. Hey, Alan.
So, Stephen, yeah, I took the picture on the left there about 3 o'clock in the morning for a project that was going on a heavily traveled DOT road. And I saw this gouge happening at the time, and then stopped the construction crew and said, "Hey, let's cut that section out to be able to make sure that we fuse it back together." And this size of pipe, which is 8 inch, through a pipe bursting process, went through and they refused this within 25 minutes. So that phrase, "when in doubt, cut it out," is what we use. They continued to move the pipe right through the pipe bursting process, and that's all they had. So as a construction observer, I would walk that pipe too prior to installation. So I'd be looking for these types of things as it moves through. That's one of the ways that we really help make sure that that gouging is not in excess of that 10% wall thickness. So
Good point, Alan. Thanks. 3 in the morning. It always happens at 3 in the morning, doesn't it? Like I said, there are productivity tools that give you alternates to dragging. There are some specifications and job site specs which will specifically prohibit dragging the pipe and require you to get it up off the ground with some kind of supports. These are official supports, pipe rollers, pipe guides, poly horses, we call them a lot of times, to help move the pipe around and reduces the amount of friction and pulling force that you need, definitely, and keeps it from becoming scratched or gouged. There's many other ways of doing it. They're probably a little less formal. People use hay bales, they use old tires, whatever they happen to have around, which could provide a soft surface to pull the pipe on, has been used as well. But these are really good tools for minimizing any potential damage. And again, reducing the overall drag force needed to pull these very long sticks and joints of polyethylene pipe around.
all right. I think Mike Whitehouse was going to come on now and talk about some productivity tools. So, Stephen, thank you so very much about site management, and we've got you scheduled for quite a bit as well. So, everybody out there,
I'll be back.
we're going to be bouncing around a bit. So, we've got a lot of. Here you go.
Yeah, thanks. So the first thing you want to do when you receive the pipe is obviously inspect it. You want to make sure that it is the diameter and the DR that is specified for the project. Looks like we've got a video here showing some of the butt fusion going on, and this is actually a butt fusion joint. Is there audio here, Alan? I don't think so. So he's pulling up the pipe into place, and you can see that they've got a string there. So there are ways to help with moving and storing and dragging the pipe. Obviously, as Stephen was talking about, we have rollers, but as a productivity tool, we also have a polyhorse system. And what that is a rack that will hold the polyethylene pipe in position for the fusion technician. And this does a number of things. As Stephen was alluding to, it's much easier to move a bundle of pipe and set it into a position than it is to pick up each individual piece and take it to the fusion machine. Additionally, while they aren't showing it here in this video, you can arrange the polyhorse so that it feeds the pipe exactly in line with the fusion machine. So you don't have your operator on the fusion machine telling a person on an excavator or a backhoe to bring the pipe closer to the machine or to push it back to get it in proper orientation. The pipe will always load into the machine in its most advantageous position. And then you also eliminate the need for having that additional personnel on the project site to run that equipment to bring the pipe in piece by piece. You can load a bundle that might have 10, 20, even 50 sticks of pipe in it and keep your fusion operator very efficient in their work schedule. Again, here we have a picture of the polyhorse, and you can see right there where they have the pipe aligned to where it's dropping into the fusion machine in the ideal arrangement and position. So there's very little movement that has to be done with that pipe as you draw it axially. And that looks like a fairly large diameter pipe, probably 36 inch or in that diameter range. So again, as Stephen was pointing out, that piece of pipe may weigh 3,000 pounds. So if you have it positioned correctly when it goes into the fusion machine, it's going to make you much more productive on your project sites. And then we also have what are called in-trench units, which are used to make a fusion down inside the trench. That was alluded to on the previous slide. And then what's really nice here in this video is the I-Series machines. And you can take those and run those from a remote controlled unit. So it's almost like a drone unit where the operator can stand remotely from the fusion equipment, away from the traffic and other hazards that might exist on the job site, while still having a high level of control on the fusion equipment during mobility. And then here's one of the in-ditch units where we're showing it going down into the trench. All of the McElroy systems have the ability to take what are called the upper works or the hydraulic systems off of the carriage. The carriage is what's used to help assist with transport and pulling the machine into place. Obviously, that can have a relatively large footprint if you're trying to fuse a piece of pipe that's down inside the trench. There may be existing utilities in the area or building foundations, roads, etc., that limit the size of the excavation that can be completed. So this gives you a way to minimize that footprint when you want to do fusion down inside the trench. And from there, we're going into above grade behavior.
That's it. Doug's here. Remember, everybody, we've got some question and answers that you can pop in there and ask for us. So that we've already had some, and real happy that you're here for us. And take it away.
All right. So when we're talking about above ground behavior of polyethylene pipe, there's a couple things we need to keep in mind. The first is the Poisson's effect. There's also thermal effects, how we're going to restrain the pipe, the effect of ultraviolet radiation on the pipe, any mechanical impact that pipe might see in a above ground installation. So first, Alan, let's go to the next slide and talk about the Poisson's effect. So very simply, if you think of a rubber band, we've all stretched rubber bands. As you pull a rubber band outward, it gets thinner in its width. And that's essentially a Poisson's effect. So if we think of that rubber band now as a section, a circumferential section of the pipe, when we pressurize that pipe is going to expand in the radial direction. Because it's expanding in the radial direction, it actually gets thinner and longitudinal, or the length, it gets shorter in the length of the pipe. So that's essentially the Poisson's effect. So most of these applications that we talk about for above ground are typically going to be pressurized to some extent. So we need to take into account that pressurization is going to shorten the length of the pipe a little bit. So where that comes into play is if we have hard connections into, say, a building or into a legacy system that may be a bell and spigot system, we need to restrain the polyethylene pipe at the ends so that it doesn't pull out of whatever we're connecting to on either end of the pipe. So again, it's pretty simple. It's something that we just have to take into account. It's how you manage it is as simple as just having a little bit of extra length in the pipe, a little bit of snake length in the pipe, so that when you pressurize it and it wants to pull in, it just basically has that additional length that it can pull out. So diagrams, this is essentially what we're looking at. So again, if you look at the lower left diagram, as we're pressurizing it, we're basically stretching that rubber band. We're stretching the hoop in the hoop direction of the pipe. That causes the length of the pipe to shrink a little bit. So again, very easy to calculate, but something to keep in mind that we don't want pipe to be tight between two hard connections, because we could have the potential to pull it out. Now, if we have to have it tight, we can take care of that. We just have to have more restraints on the pipe to make sure that we're not pulling it out of either a fixed connection or some type of a bell and spigot legacy pipes. Next slide. So pipe's going to be above ground. Anything that's black, and typically we're going to be talking about a black pipe, is going to get hot in the sun. Polyethylene being a thermoplastic material, its properties change as it gets hotter. So next slide. So good thing about polyethylene is that in any climate that a human is going to be comfortable in, polyethylene will maintain its ductility. It will be in a, I don't want to say rubbery state because it's not like a true rubber material, but in terms of impact resistance, flexibility, things like that, it's always going to be in the same state from -40 Fahrenheit up to 140 Fahrenheit. So really any condition that a human would be comfortable in, polyethylene is going to be comfortable in. Very cold temperature applications, again, not an issue. Should you have some type of an impact, the pipe is not going to shatter. It's going to deflect. It's going to absorb some of that impact. So again, it's a very ductile material over the temperature range that we are going to be using the pipe. Next slide. One thing to keep in mind, though, is as temperature increases, so the temperature of the pipe increases, the pressure resistance of that pipe decreases. And so you can see this in the blue line for a DR11, the orange line for a DR17 dimension ratio. It's going to drop. The good thing is we know exactly how much it is going to drop, and that's what the chart here is telling us. So we know that we're going to say at room temperature at 73 degrees Fahrenheit, we may have a pressure of 200 PSI for a DR11 pipe as a maximum allowable operating pressure. When we go up to 140 Fahrenheit, that drops by a factor of 0.63. So we're now down around 120 PSI, maximum operating pressure. So when we think about above ground installations, we always want to consider what's the maximum temperature that the material is going to get to. Now, the fluid going through it may be at a colder temperature, but what we're concerned about is that ultraviolet, that sunlight that's hitting the pipe is going to warm that pipe up. And 140 Fahrenheit is kind of typical for most climates in the summertime, or full exposure to the sun. So again, we know how it's going to behave, and we can easily design for that. Just don't expect a 200 PSI maximum operating pressure pipe at room temperature or at 73 Fahrenheit to be the same at 200. It's not. Next slide. The other thing we have to consider with temperature is that polyethylene will expand and contract based on the change in temperature. We understand how much that change is going to be. The calculations that we show here are a fully unrestrained system, which means that there's no effect of friction because the pipe is typically going to be laying on something. This assumes that the pipe is in the air, that there is no friction upon it, and that it is an instantaneous change in length. That's not actually the case. Polyethylene will slowly warm up. It will slowly cool down as we go through the day. So we have to keep that in mind. We want to basically install the pipe so that we have ability for that pipe to move, to expand and contract as it needs to with temperature. Again, it's not difficult to do. It's easily calculable, and this equation here actually gives an unrealistically worst case scenario in terms of what the expansion and contraction is going to be. Typically, you have frictional restraint on the pipe just because it's sitting on the ground. But again, it's roughly 1 inch per 10 degrees Fahrenheit per 100 feet of pipe. When it expands and contracts, the other thing to keep in mind is that polyethylene is a very flexible material. It has a low elastic modulus to it. So it will expand more than, say, a carbon steel pipe, as you can see in the diagram below. So instead of 3/5 of an inch, it's expanding a full 8 inches, but the force that's being applied as that pipe expands, so if it's pushing up against a building connection, for instance, is only about 321 pounds instead of the 8,000 pounds that a steel pipe would expand. So again, you're in a better situation with polyethylene because it's while it does expand more, the force that it's applying is significantly less. And also as it contracts, the force that it's pulling to contract is also significantly less than you would see with a steel or a higher or a cast iron, ductile iron type system. And now I'm going to invite on Mike and Stephen to talk about restraint, because I'm not the expert.
This might be part of the section that might be a free-for-all for us here. So typically what we're seeing here, this is a pull from an old design guide that I found. Essentially, these are thrust blocks. And what a thrust block is, it's different than a anchor block, and we'll really get into that quite a bit. A thrust block is aimed at addressing some type of pressure surge within a system to support that water hammer that comes in to make sure that the bell and spigot pipe doesn't pull off from that location. Since the butt fusion joint is a fully restrained joint, any type of water hammer happening against that joint, if we had a change in direction or something like that, but the way to connect it was actually fully fused, we're not going to blow that off from a water hammer standpoint. So all of these are now going to be eliminated, and we're going to focus on what we call anchor blocks, which is a terminal connection to other restraints as we go through there. So Mike, I don't know if you want to elaborate for us what we're looking at here, but that's essentially what I just summarized for us. Do you have anything else to add to this? This is a pretty unique application going from buried to above ground. And here, these are fully restrained joints. And by the time that we have to connect at these flange locations to another type of transition, then we have to make sure that those are fully restrained joints as well.
Sure. So if you have a bell and spigot system, when you have internal hydrostatic forces, it tries to take that elbow and straighten it out due to those hydrostatic loads. And that can create a separation in those systems that are joined by the bell and spigot. Since the polyethylene is a totally fused system, it is considered to be self-restrained when joined through fusion methods. And that is recognized by AWWA, by NFPA, by the Plastics Pipe Institute, and by the manufacturer. So we are eliminating the need to pour concrete on these elbows during the installation. And even when you have installations that are above grade, you don't create enough axial force in the pipe to damage it or to pull it apart. It is always a self-restrained material when joined through fusion. What you need to be cognizant of is when you join to a fixed connection or when you join to a material that has less resistance to axial pullout, you may want to create an anchor block to prevent the polyethylene pipe from moving.
And here's the anchor blocks. Let's talk about those.
Sure. So there's the anchor block, and you can see we have two different methods that we use to help take the axial loads in the pipe and transfer them to the anchor block, and then from the anchor block to the surrounding embedment materials. And for a new project, we would typically install what is called a wall anchor, shown there in the center image, and that can be butt fused to the pipe as you are installing it. And then once the wall anchor is there, of course, you can place it in a thrust block. And the thrust block is sized upon the amount of axial force that you anticipate in the piping system, and then also on the allowable bearing strength of the existing soils or the embedment materials that you use. If you find that you have a system that's already been installed and you need to come back and provide thrust restraint to it, what you can do is put on what's called an electrofusion flex restraint. And each one of those are rated for a 7,000-pound load, and that is at a 2-to-1 safety factor. So again, you determine what the axial force is that's anticipated in the piping system, and then you put on the number of flex restraints that are required in order to exceed that axial load that's anticipated. And these can be arranged in any manner around the pipe circumferentially. They can all be on top of the pipe in a row, or they can be placed at 90 degrees. The orientation is not the important thing here. What is important is calculating the axial forces. And while the axial forces or the stress in the pipe wall are very easy to determine, the harder question in a buried application is how much frictional resistance do you get at the pipe soil interface. So oftentimes it becomes not a pipe stress problem, but more of a geotechnical problem. And if people are concerned with restraint of their pipeline, I generally recommend that they use a type 1 material, which is crushed stone or compacted sand, and you have a very well-known pipe frictional factor with that. When you start using existing soils, whether it's high in clay content, low in clay content, et cetera, can really change that frictional force at the pipe soil interface. And that's actually another class that the PEI Alliance offers on burial restraint.
So I'm going to take half a step back. So Doug was calculating the expansion or potential expansion, and then we're taking that potential expansion into a force, the force required to restrain that expansion, and that varies based across the modulus of elasticity of the pipe, but also the cross-sectional area of the pipe. So if we get to a bigger pipe, now we're having a thicker wall, and we'll have a greater force through it. It's possible in your above ground applications now that we can bury part of that section with these electrofusion thrust restraints if we wanted a formal anchor block at the end to stop any movement through there. And then we can just calculate how many of those we need based on Doug's equations. Is that about right, guys?
That is absolutely correct. And
Yep.
one of the hardest things is to determine what is the most appropriate modulus to use for your thrust load. Because if you use an instantaneous modulus, you're going to have a very high thrust load. But if your thermal changes are driven by seasonal environmental changes, then your modulus is relatively low. Typically, they use 50,000 psi for a modulus for changes that are driven through environmental seasonal. Now, if you have a pump that kicks on in the Arctic Circle and it's a minus 120 F outside and your discharge water is at 100 F, then you've got a very high modulus and you need to use more of an instantaneous. And that modulus directly affects the force that's calculated on the end anchor.
That
Very good
also
point, Alan.
then forecasts for us, does some foreshadowing. The assumptions that we make, the temperature assumptions and fluctuations is extremely important. So Doug also talked about the theoretical being instantaneous, but actual observed might be half of that. So having done some of these myself, as well as Doug and both yourself, Mike, that's probably one of the key questions is what is the actual potential observed temperature change as we go through? Okay, so what are we looking at here? Obviously, this is buried in that connection. Is this just poured concrete around that anchor block as we're looking through here, Mike? Yes. So we would just set that up and you'd pour your concrete in around the anchor blocks. In some places, we want to make sure that that's properly sized. And I think we've got a little bit of a calculator here for us. Anchor blocks for HDPE water pipes. This was a report in 2022. Do you want to tell us a little bit about it, Mike?
Sure, that was written by Dr. Belkin, and it was actually based on frictional studies that we did at the Bureau of Reclamation, where we took polyethylene samples and tested them in accordance with the various embedment materials that are commonly used. And then from there, we went through and looked at the amount of stress relief that occurs in the viscoelastic material, because as a viscoelastic, it will shed those stresses over time and they will reduce. And this is the final report by Dr. Belkin, and it doesn't involve some fairly high math. You have to do a solution of the least con. I'm sorry. You have to do a solution on the integral for least finite squares, and it is about a 41-page report. So it can get complex in the evaluation, but at the end of the day, it's very uncommon for buried pipe systems to move unless they're buried extremely shallow or unless they're embedded in extremely weak fills. And typically in a deep bury application, you'll have full resistance from frictional resistance within 15 or 20 feet.
Yeah, absolutely. We're getting a lot of great questions. Everybody, keep it coming. There is a calculator for you that PPI offers here, the HDPE app function. So you can go online and be able to look at these. The industry on whole is fairly conservative. So they may come back with a rather large anchor block or something of that nature that you want to take a look at. I believe it's also limited to a 24-inch pipe diameter as well. So when we start to look at some of these larger changes in temperature, larger pipe diameters, now we're going to go and look towards an experienced engineer that can really help make sure you evaluate the local temperature fluctuations appropriately and have done this before. So this is just a guide for you to be able to take a look at to see if it's something that's going to cause a problem. So I don't know if either one of you want to tell us about the MJ adapter, but there's a video for it here. Stephen, if you want to opine.
Yeah, so MJ adapters, these are great tools for adapting to a ductile iron fitting and or an appurtenance such as a valve or housing or anything like that. So these are a fused on MJ adapter, and they're fused onto the end of the polyethylene pipe with the backup ring pre-installed on there. Don't put it on later. And then the gland is put on. You can see here, you got the conical gland, and it goes into the mechanical joint just as it would any other type of fitting. This is the preferred method to join polyethylene to these types of systems. There are some fully mechanical MJ adapters. Those will work. Typically, I would say 12-inch and below, they work very well. You get above that size. It depends on the manufacturer. But the recommended best practice is to use a fused on MJ adapter to get the best performance and constructability.
So we got a question earlier, Stephen, about mega lugs versus MJ adapters, and one of the biggest difference there is the mega lug, if I'm correct, actually
Yep.
puts an axial load on the outside of the pipe through this, and then it needs an insert stiffener to be able to stop the bolts from pushing into the pipe.
Correct.
A MJ adapter like this goes longitudinally across the pipe, so you're distributing the forces completely different. Is that correct?
Right. Yeah, that's absolutely correct. And like I say, the Megalug is a fully mechanical MJ adapter. It needs the restraint, so it does have the bolts that go in and actually compress onto the pipe to give you that restraint. But you do need the insert stiffener for that as well for long-term performance. Typically, again, a 12-inch and less, those work pretty well. Above that, going to a MJ adapter that's fused on is the preferred method.
Okay, this also works under wet loading conditions. So if we have a water main failure, there's a lot of what out there? Water, right? So this is one of
Always.
the things that helps. We were asked about mega flange. I'm not that familiar with mega flanges, but just flange adapters, if that's what is meant there, is similar thing to this MJ adapter as
Yeah.
we've shown. And you just have a flange backup ring, and we have a gland if we need it to connect to a different type of pipe material or something other. And I believe our pre-show video showed a little bit of that, correct?
It did,
Steve?
yeah. So again, you're looking at the difference between a mechanical flange adapter, such as a mechanical MJ that we talked about in the Megalug, and that's going to be the same thing. You're going to have to bolt that on. It's going to have to be restrained. You need an insert stiffener in the pipe, and then it acts as the flange on the pipe. The preferred method, again, is to just fuse on a flange adapter onto the polyethylene pipe with a pre-installed backup ring, and that way you get a fully restrained joint from the flange adapter that way. There's also a great PPI technical note, TN38, on bolt torque using flange adapters. So if you are going to be using that, I recommend getting that document so you torque the bolts on the flange to the proper amount, come back and retorque them the next day to make sure you get that long-term seal.
Awesome. So we did have another question as well as to whether or not every MJ adapter needed a stainless steel insert, and that depends upon the manufacturer of that particular fitting itself. So this is a fairly robust fitting, that MJ adapter, and each manufacturer would have a different recommendation for you based on their design of their fitting themselves.
Right.
So
The
now
smaller diameters, a lot of them are going to be pre-installed. The insert stiffener will for it. Larger diameters, it'll be a separate piece many times, and you can choose according to their recommendation to use it or not. But guidance is to say use it if in doubt.
Okay, good. Now, I hate to bring Doug back on for this with the dead frog. I can tell you that Doug definitely did not kill the frog or take the picture, but that just shows that the pipe can heat up over time period. So go ahead and talk us.
Yeah, so we typically prefer the black pipe because the carbon black will actually act as a UV absorber. So it will take that UV energy and turn it into heat. The downside, or if we look at the stack of pipe on the right, that's a PVC pipe. And PVC is very sensitive to UV radiation. It causes a process called dehydrochlorination, which is that brown, rusty look to the PVC pipe. That is what happens if you're not properly stabilizing. But with polyethylene, with black pipe, it's really indefinite outdoor use. It's the same carbon black that is used in telephone wires in order to keep the UV stability and the coating on the telephone wires, which is polyethylene, by the way. So we know it works. We know it's going to give us a long-term outdoor stability that we need. We do also offer pipe in other colors, polyethylene pipe. You would have blue for potable water. You might have yellow for natural gas applications. Those are typically 3 years of outdoor UV storage. And after that point, you may start to get some degradation to the pipe. But if it's black, it's really indefinite storage.
Hey, Doug, real quick. So earlier we had a question on that. There was a question on the UV stability of a colored stripe on black pipe. And that's a good question. So typically the stripe itself is UV protected chemically for 3 to 5 years. But remember, even after that amount of time, the stripe is not 10% of the wall thickness. It's less than that. So even if it does fully degrade for whatever reason, it will not cause any detrimental effects to the long-term performance of the pipe because it's less than 10% of the wall. So that it will not cause any long-term performance degradation.
Right. And so the stripe may fade
Right.
over time, which is what you're going to see, and it may get flaky as it starts to degrade. But you still have the print line that's going to tell you what the pipe is and what it contains. So in general, from a stripe, it's not really an issue. And the assumption is that you have about 3 or so years worth of UV stability in an outdoor application for the stripe.
Right.
So how does carbon black act? Well, what happens is that UV energy comes in step number 1, and it hits the carbon black particles. And what the carbon black is, it converts that UV into vibration. So they heat up, it causes the particles to vibrate, and that basically gives off heat. So part of the reason that the pipe does warm up in the sun is because of that carbon black, and it's taking that UV energy that would be detrimental to the pipe, converting to thermal energy, which is less detrimental and essentially has really no detriment to the pipe at all. So that allows us to give that UV stability, and carbon black doesn't degrade as it's being hit by the UV energy. So it's going to stay there. As long as that pipe is black, you have your UV protection, and it's going to stay black. As I said, here's the proof: telephone wires. Bell Laboratories back in the 1930s did a lot of work, found that carbon black at the level that we added is a very good UV stabilizer, and maintains the physical properties of the material as well. So again, where's the proof? Well, almost every mining application, the polyethylene pipe is sitting above ground. Landfill operations for degassing and dewatering landfills. Power cables. Here we've got geomembrane, which is polyethylene with UV additives as well. So a lot of different ways, a lot of different proof that we have that this does work and that this does maintain the physical properties of the material. This is another example in San Lorenzo Valley in California. They were going through an ecologically sensitive area for water lines. You can see that there's, I think, 3 water lines here that they put above ground. Well, they had a wildfire come through, burned up all the pipe, burned up the forest. They came back in and basically put the lines back in because this is an above ground application. You can see that they're suspending it. They've got it on wood supports. So if that pipe has to move a little bit, it's on a relatively soft or a softer surface than the polyethylene itself. And they have it properly supported so that you're not getting any significant bellying of the pipe as it goes down the line. Inventory yard as well. There's no need to cover the polyethylene. The black polyethylene pipe, if for some reason you are using blue or another color, gray, for example, you would want to cover that in storage until you actually get it buried. In the above ground application, really what we recommend is the black, because sometimes you don't know the actual length of time that is going to spend above ground. We have our construction plans, and then we have reality, and sometimes they don't meet. One last thing, if you have any fittings, especially electrofusion fittings, you want to keep them contained until you're ready to install them. So we saw the video earlier of the corporation saddle that was being installed. I think that was in the intro video. Notice that the operator took care to take that fitting, flip it over so that the fitting and surface that's going to contact the pipe was not in contact with any dirt, and also made certain to keep everything clean. So we want to keep our site as clean as possible, especially with fusion or electrofusion. With mechanical fittings, it's not as important, but it's still something to keep in mind.
Yep. We've had a lot of good questions here, Doug, and I'm actually going to like tear through them real quick so we
Okay.
keep everybody going. Does PE pipe bend, curve, and storage due to sun heat? If then, do we need shade? All of those HDPE pipes will be subjected to the same amount of expansion together because they have the same amount of behaviors, in which case we certainly do allow spacing between each of those areas of pipe that we are storing in that process. Doug's mention about keeping everything wrapped in the package that it came from protects that from the elements itself. Another one, we had a client that is worried about vandalism with above ground temporary installation, namely fires as a concern. How can it be mitigated? So for temporary installations, you'd come back if there's some type of vandalism and then maybe fix exactly what happened at that time. The flash point of HDPE is to which case it catches on fire is upwards of around 650 degrees Fahrenheit, if I remember correctly, in which case we hopefully they don't work that hard to set your pipe on fire, but there's not a whole lot that you could stop about that, Doug. I don't know if you want to.
Yeah. So polyethylene will burn. It's not easy to ignite, but it will ignite. I mean, if somebody decides to throw a road flare onto a stack of pipe, it's going to burn. So, vandalism, they say you can't fix stupid. You can't really prevent the vandalism. The photo that we've got here, I think Alan likes to say this was the town drunk, who went off the road and rode on top of the pipe. And you can see one of the wheels of the car sitting there. Again, this would be one of those applications where you cut it out and you fuse it back in. And so you could use electrofusion couplers or things like that when you talk about damage. Typically, what we're going to see, and we have a video from Sunbelt Rentals that I think is on our website or on our YouTube channel, where they use K-rails or Jersey barriers to kind of protect the pipe that was running alongside a road on a sewer bypass. So those are the kind of the things to keep in mind. The nice thing about polyethylene is that from a taking it to your scrapyard and getting money, you're really not going to get a lot of money for it. So it's not like ductile iron or brass or copper where there's an intrinsic value to somebody stealing it. Polyethylene has less of that going on. I mean, it is recyclable, but you're going to get like a nickel a pound. It's really not worth somebody stealing the pipe. Again, it will take some damage. The photo on the left was from, I think, Livonia, Michigan, maybe. And this was a sewer bypass line that they had to run down the middle of the street. And you can see that they were making sure to put up barriers alongside that. Same thing, it will take some abuse with the backhoe, the bulldozer here going across it. If this is a constant crossing, then you want to put over a trench plate. Or somehow take it underground, drill it in underground on crossings. But it's fairly easy to mitigate any damage or mechanical impact that might occur.
Okay, we have quite a bit of ground to cover, and I'm going to kind of move quickly through these next series of slides, and we'll have some more information at the end there. Love the questions that are coming through. Thank you all very much for us. We're going to talk about at-grade temporary, at-grade permanent, bridge abutments, and any type of anchor support design. So everybody's been pre-leading some of these questions, or your questions have been pre-leading some of these answers that we're going to give you here. And I hope everybody's listening. So definitely we can tell that you're fully engaged in thinking through these process. And thank you so very much for your time to spend with us. Again, the Q&A is here for you. And then also at the end of the webinar, the best way to get your CEUs and PDHs is to complete the survey. That's the quickest way to do it. If you just email one of us and say, hey, I didn't get that, it takes quite a bit longer for us to do it. We'll get to you as soon as possible. So one of the most used portions for above ground above ground pipe here for high density polyethylene and municipal water systems is temporary bypass, whether or not that be a temporary sewer bypass or a temporary water bypass. These are some of the things that we're going to walk through of what we're looking at. In potable water, what you'll see here is a fusion run, 8-inch, that they fuse that whole long run beforehand prior to the pull, the pipe bursting pull. And then behind that, we have 2-inch pipe that simply is disinfected after fusion. And we'll pull that through from one neighborhood to the next and simply reuse this pipe as that project progresses. That we want to make sure that that pipe is protected so people aren't driving over it and damaging that pipe or things like that. But this process allows us to reuse and reuse and reuse that pipe material to be able to progress through and use as the temporary bypass as we see fit. In wastewater, sometimes those are larger. Depends on whether or not it's a closed system, which means the wastewater does not have the addition of storm water typically to it, or an open system. An open system has a combined sewer. So these are typically older cities that have developed from an older time period, and they combine wastewater with storm sewer in some instances. And then they become significantly more difficult to be able to size through bypass. Now, as we go above ground and we have a force main, we do have to look out for entrapped air, which you'll see here as an air release valve. Essentially what that does, if at that high point, if that force main material is releasing hydrogen sulfide, releasing other things, that's gases, that is compressible gas for us. Now, water and wastewater is not compressible. It will accumulate at a high point and then stop the efficiency of us moving that force main material here. So that's why one of the reasons we make sure that we size those and place those air release valves at the correct location at the high point. Also, contractors can get pretty creative from what you're seeing here itself through this stormwater structure as they come through and put it through. Here is a prime example of a very complicated temporary sewer bypass. I'm not sure that I have the video. I may very well advance to it if I do. But this, a rehabilitation of 78-inch pre-stressed concrete cylinder pipe, about 4,700 linear foot, took 8 lines and 45,000 linear feet of 24-inch HDPE to be able to fuse together. So you're seeing all of these pumping units. We want to make sure that we have capacity for the gravity sewer that we understand goes through there in a diurnal pattern. What that is people that go to work in the morning, they're using it. We have higher flow, and then people that come back in the evening, there's higher flow in that pattern, but it's predictable. It's the storm sewer component of it that requires us to try to have some type of a rational prediction in the history of rainfall events, which can easily make this a larger system than if it was just a closed system in that manner. So this was a fairly substantial project. Now, the actual CIPP lining was significantly easier than the sewer bypass as you see this, but they took all of that HDPE and just put it above ground, and then they were able to move that down on the other side of the rehab and go through it. Here's a video I'm going to talk you through. So a lot of these items and a lot of the things that Stephen mentioned about moving it to and fro, about fusing it together with the equipments. We've had some questions if it can come off the chassis or not. All the equipment is designed to do that. Rollers. This shows a proper use of forklifts that Stephen alluded to. We're understanding how these things need to move and shift together based on what Doug told us with above ground expansion due to thermal effects and Poisson's effect. Each of those locations that we have are a restrained connection to that manifold. That manifold is something that is custom made for these particular locations that Mike Whitehouse and ISCO can really provide you in that area. They can fabricate that for you to make sure that we have all the connections that we need with all the valving. And this is a safe use of high density polyethylene that can be used and reused based upon that carbon black that we've added to it for above ground ultimate UV protection. So this particular video ties in everything that we've really talked about in a large scale application that shows they understand people understand. We understand how to put this on a steep slope, which was one of the questions we've been asked as well. That weight of the pipe, if it's coming down the slope, how often do we have the spacing? My favorite thing about some of these is you are also asking that question and you're very engaged. So thank you very much for doing that for us and being able to help make sure that we're leading through these webinar questions and presentations that we have. Definitely tells me that you're paying attention to that through this process. So at grade permanent, these are some valves that were installed. We're allowing that pipe to really move through it. Here's another example of a larger machine. This is an Alaskan installation in Alaska, and that's the Talon that moves through this itself. They elected to have orange pipe in this area. Doug or Stephen, can you tell us if orange pipe is manufactured in the United States and why we might want orange pipe? I believe it was above ground, so we want to be able to, if it's remote, maybe take a drone and find it. I don't know. I'm guessing here. What do you guys think?
So orange pipe is typically used for gas distribution applications in those countries that use the ISO standard system. So it's an indication of a P100 or what we call a P4710 material. In this particular case, this was a buried application, but my understanding was the only available pipe that they could find, because I think this was in Alaska, and so you have a very short construction season. The only available pipe that they could get in the size that they needed was orange. That was my recollection of this particular job. So it's not a color that's typically available in the United States in pressure pipe applications. You will find it in conduit applications. But this just happened to be to fit their construction window, this was the pipe that was available.
So from a resin standpoint, is there much difference between the 4710 and is it the PE100 that's the European counterpoint?
There's really not much of a difference between them. Pressure ratings are a little bit different just because the systems are different, but most 4710 materials are also PE100 rated materials.
Okay, good. Very good clarification. Mike, you want to come on and tell us about some of the controls that we might have through thermal expansion? And everybody, feel free to stay on if you want and opine as we need it. What are we looking at here, Mike?
Sure. So we've got really three different methods shown here. At the bottom, we're showing a conventional expansion loop, and that can help to take up the axial movement in the system if you don't have a method or a means to withstand the total axial forces. You can also use an expansion and contraction coupler, but what's important to remember is to make sure that the activation force on that expansion and contraction device is lower than the allowable buckle for the polyethylene pipe, because as a flexible material, it will tend to buckle or deflect laterally, as you see in the top image during thermal expansion. And really, this movement that's shown in the top image is a benefit to you if you have the room and availability in above grade application, because as the material moves or stress relieves itself in lateral deflection, it lowers the loads that are on your terminal end anchors. In the middle, we're showing a system that has guides or bollards. And again, those are placed to prevent lateral deflection based on Euler's law. And in those applications, all of the force is going directly to the end anchors. So the way I like to look at this is when you put more heat in the pipe, you're increasing the energy in the system. And that energy either has to go to your end anchors, or it has to be relieved through thermal strain, as shown in the top figure, or through an expansion and contraction device such as a loop or a fitting.
Okay. And here's some various mechanisms to be able to restrain this pipe. Do you want to tell us a little bit about these?
Sure. So these are methods that you can use intermittently instead of an end support. And those can be helical anchors that are going down into the ground. And again, that the strength of your soils or embedment materials will dictate how big that anchor has to be. You can pour concrete blocks that just have a mass or a weight that's so great that the pipe again can't move axially. Or you can replace those concrete weights in the straps with a berm or an embedment material. And oftentimes you'll see above grade applications with piles of dirt intermittently along the line, again, to help control pipe movement.
So that is in areas that potentially we don't have as much right of way that we need. We want to try to keep it going. And then there's also creative ways to try to think of a lowest cost option for a contractor. One of the big things here is any type of strap around the pipe from a metallic connection. We need to have a rubber gasket within that as well to make sure we don't damage it. So we do know how to calculate the deflection as thermal or supports for the deflection from if we're having thermal additions, we're moving that along. That's based on the function of what Doug told us a little while back. But here's some essential for you for what we're going to see deflections at the strain connections, and then we'll calculate the strain from what that deflection might cause at those particular comparison points here. So there are calculations to be able to show us what we need to do there. PPI's handbook on polyethylene pipe has a good bit of that. Tell us how we might be able to hang this on bridges or piers now, Mike, as we come through.
Sure. So this is an application showing a bridge hanging, and typically when they do these, they will install the pipe on one of the warmest days of the year. And when they do that, what it does is it ensures that the pipe is always in tension or from contraction during periods of thermal cooling. What could be problematic is if you install this on a very cold day and then the pipe started trying to expand and deflect laterally. So now you're putting a lot of strain on your support brackets.
Okay. And then here's again, we're looking at that support spacing design, anchor and support design at the terminal connections through that. And we want to limit deflection. Now, in pressurized pipelines, it's really a visual thing that we're looking for. But if you've got gravity going across a bridge like this, we certainly want to look to make sure that we have continuous flow and no sumps that might otherwise accumulate. So then here's some of the examples of spacing designs. What might be we looking for here, Mike?
So what you want to do is limit the deflection to it's recommended to 1 inch at mid-span to maximum deflection. And that does two things. It helps to prevent the belly as shown in the bottom of the pipe. And that could be very important if you're in a sanitary sewer or something where you don't want to have solids collecting in the conveyance pipeline. And it also limits the stress loads at your anchor so that you don't have to worry about deflecting the pipe. And typically you'll want to surround the pipe around 270 degrees with that bottom anchor to prevent deflection at the very base.
And then this one's how we go about calculating that max allowable bending stress. And this is at those connections itself. So if we have that thermal expansion or even weight of the pipe, that would have to be looking at if we're hanging it on a bridge. Both of those things come into consideration. We look at the allowable bending stress, which is a comparative to the allowable tensile stress within the pipe itself. So we do have calculations to be able to show us that, as well as that deflection. Traditional beam analysis is what we're looking at here in the bottom right. We do have the calculations to be able to go through there. The Alliance does have calculators for you as well that do this for these assumptions if you want to reach out to us to be able to share that with you. So some of the main things that we talked about, Mike said 120 degrees of that pipe diameter. So we want to support quite a bit of that pipe diameter as we go through. And here's a lot of different options. I'm going to move pretty quick because we're at 3:15 right now. So this certainly shows some of the options for you in this manner. And there's lots of different specialty tools out there for you for these fittings. in order to be able to provide what we've got. So, Stephen, Doug, come back on for a couple of last words. If we got it, we may not have been able to get to all your questions today, but thank you very much for throwing them at us quite a bit there. We really love it. We tried as hard as we could to be able to answer while all of this was going and still pay attention. So, multitasking is something that we definitely strive to do in the best of our ability. Anybody want to take it first here? Stephen, Doug, or Mike?
I would just say, if you have further questions, we are a team and we are here to help you, and reach out to any of us. If you happen to reach an individual that may not have the specific answer, we'll consult with each other and get you the answers and the information that you need.
Yeah, don't be, you know, I get this a lot. People that haven't designed or used polyethylene pipe are always concerned because they look at this theoretical thermal expansion contraction calculations. They're going, oh my gosh, it's going to move all over the place. Don't worry about that. Those are theoretical calculations. It's normally much, much less. And if you need to anchor it down, it's easy to anchor down. If it can't move at a certain connection point, it's very simple to mitigate that and make sure that you have a static point to connect your valve housing to or whatever it might be. So there's lots of ways to do it. There's lots of history and experience doing this. So don't be concerned about it. It's a very successful type of approach.
Happens
Yeah,
all the time, every day. Yep. Go ahead, Doug. Sorry.
Yeah, the other thing is I would recommend you look at the HDPE app. So this is an online calculator. We've kind of touched on the theoretical. The calculator makes it very simple. The other nice thing about the calculator is that you can click a button, and just like when you were back in school and they said show your work, it will show you the work. It will reference the different references, tell you what values it was using, everything. So the calculators that are available up on the PPI website are invaluable, and make things very easy, very understandable. So and it allows you to play around and say, okay, well, what if I went to this size? Would it work? What if I did this? Would it work? So definitely use the calculators. It makes things very simple. We're just trying to make it understandable to everybody.
And Stephen, Doug, Mike, you guys nailed it as normal. So thank you so very much. You certainly excel at answering these questions and providing lots of great communication for it. So, all right, we'll see everybody later. Thank you so very much. The next
Thanks for
one
your
is
time, everyone. Have a great afternoon.